Today we are going to talk about the parallel algorithms, parallel applications. So we are going to introduce 4 applications: parallel reduction, prefix sum, also called SCAM, histogram, and convolution. So these are the parallel. So first is parallel reduction. It's a popular class of the computation. So we will see the reduction tree, which is important to understand, how the reduction work. So you can do parallel reduction. You can do reduction across different operations. So the common one, you can do sum, math. So in that case, you have a list of a number. You can find the max number over this list or the minimum number. So these are the operations you will do on this list of number. Before you start doing the operation, you need to initialize the result as identity value. So for example, if you want to do the sum, or for example, we do try to find the max number. So what will be the identity value? So the identity value will be the smallest possible value. So if we say all the numbers are positive and integer, so that will be 0. So each number will compare with 0. Once it's bigger than 0, it becomes the current max number while doing the iteration. So the identity, you need to find your identity value according to the operation you do. Let's do an example. So this is for find the max value from this vector. So I will stop share this, and I will share another screen. Can you see this slice? It's still the parallel reduction with the vector. Okay. So I will do that manually. So I compare 2 by 2. So this is for 3, 7, 4, 6. This is one iteration, so I call it step 1. Then I do the next step, still 2 by 2. So that is 7, 6, step 2. And I do the last step 3. So what I want to induct is the number of operations I do. So here, for the first step, I do 4. Is the number of operations. So here I do 2. Here I only do 1. So this is 4 is the number, is the size of the vector, the number of elements divided by 2, then divided by 4. Then this is divided by n. So if you plus them, it is equal to n minus 1. That is the number of operations you will do in order to find the max number. So how many steps? So you can see here is the log n. The n is 8 here. So if you use thread, you can have 4 thread 1, but thread 0, 1, 2, 3. So at the first step, each thread will do one comparison 2 by 2. But at the second step, only the thread 0 and thread 2 will do the work. Thread 1 and 3 will be idle. So at the third level, only the thread 0 will work. So we will discuss how to avoid a little bit this idle. Some of the thread couldn't do work during the computation. So I talk about the number of operations we do. This is if we do the sequential comparison, still the operations you do is still minus 1. Like if you compare your identity with 3, with 1, with 7, all the way to the end of the element, still n minus 1. But definitely, if you do it in a for loop, you will have more steps. But here we reduce the steps to log n. So this is the, I think this is do the sum. It's similar to what I described before. So I will shift back. Yeah, so let's think if we have 1 million input values. So if that's log n steps, that it takes 20 steps. But so one thing you may interested is the average parallelism. So it's the number of the operations you do divided by the steps. So it's the how many, so in average, each steps will do how much work. So for 1 million input numbers, the average parallelism is 50/100. However, the peak resource requirement is still 500,000 because you have to, so at the first step, you still need to compare 2 by 2. So 1 million divided by 2, so it's 500,000. So the amount of work is comparable to sequential, as I said. So let's see how it works in parallel. This parallel reduction is very common used when processing the large input data set. Because there are several benefits, it's no required order of processing, so it is associative and commutative. And the partition, the data can be partitioned into smaller chunks. Each thread can handle a chunk. Use the reduction tree to summarize the results from each chunk into the final answer. This is a popular algorithm. So you are given a list of number and you are required to find a number to summarize this list. So like the MacReduce framework are the examples of this pattern. Next, we will focus on how the reduction tree steps work. Yeah, so there are some challenges on the GPU side. For example, so I will do an example. So if we have a list of number 1, 2, 3, 6, 9, 8, 9. So we do the comparison between 2 and 2. So we get 2 here. But for this, but in this position, we still have 2. And this position, we still have 6 and 9. So this is one data structure. So after we compare it, the results is still right back to the same data structure. So you can see this one is still there. So the problem is when we have multiple threads trying to write back to the global memory, it can cause problem. Can cause the collision. So one idea is that we bring the data to the shared memory. So each thread has a private output location. So they don't need to directly write back to the global memory. So after we write the intermediate results, then we use the reduction tree to compile the values from these private locations to the original output location. We will see it in details later. So this is an example how we bring, like as I said, we try to bring the data in the global memory to the shared memory. Here we define a shared array. This is the shared memory array called partial sum. The size is the 2 times the block size. So I can show you some. So this is a straightforward way to see how this code work. Basically, it's just you make each thread loads 2 elements from the global memory to the shared memory. This one is the shared array. So I will go back to see the code. So the T is the local thread ID. So we try to find where is the data in the global memory. So the input is the data we have in the global memory. So we find the position that thread want to access. That's here the second, the third and the fourth line is just bring the data from global memory to copy the data to the shared memory. This is an example. We will see how it works in a later example. I think I will switch. What you see here, this snippet of code is the kernel, is what will be executed by each thread. I think I still need to do an example how it works. That's so I still use the example I will write here. It's the 1, 2, 3, 6, 8, 9. Well, I think I have a example here. So I will try to use this example. That's 2, 6. So here there's the for loop. So each thread will do several iterations. How they this is for the summation. So still I need to, that's thread 1, thread ID 0, 1, 2. So the first iteration, the stride is 1. So the stride is important here. So each thread will participate, not each thread. So each thread will perform, each thread will operate on the on current element and its next element. Like thread 0 will compare the element 1 and 2. So that is the first level. That's level 1. So each thread will perform these operations. The operations is here. Since stride is 1, so all the thread ID modules, the 1 is all the thread ID, module 1 is 0. So that's why all the thread will work. Actually, it's thread 1. I think it's here. This is thread 1, thread 0, 1, 2. I think I can add more. So each thread will participate. I will add more threads. That's so. So at the second iteration, the thread, the stride become multiplied by 2. So only the thread ID who module the stride equals 0 will work. That is thread 0, thread 2, and thread 4. So thread 0 will compare 3 and will operate on 3 and 9. The thread 2 will operate on 17 and 7, and another thread 4 will operate on 6, and there might be other numbers. So finally, the thread will come to only, so as we said, we draw before, so once the stride become the max number, so here is, so in this example, we put all the numbers we would like to operate in one thread, in one block. So that's why the number of numbers, the number of the number of numbers is the size of the size of all the numbers is the block dim. So I will finish this example. So that's here we have 6. So here, I think use this example will be better to see how the stride change as the iteration goes. So the first line is stride 1, and so here it's, yeah, the thread ID is in this orange circle. So you can see in this case, in this case, this shared memory contain, so we put all the data we would like to operate in the shared memory. This is 2 times block dim. So it's, I think it's 16. So that's why 1 block dim is 8. Here is the last iteration in this for loop. Here comes another question. So what happened if the warp has more than 16 threads executing? So the answer is it will have shared memory bank conflicts. How do we present this? So in this case, we can think there are 8 threads here, 8 threads. I will still use the 32 threads example. So first, the shared memory banks are organized that successive 32 bits words are assigned to successive banks. So the bank width is 32 bits per bank it's the 32 bits per bank per cycle, per clock cycle. What I said is, you can see this is a bank, and there are 16 elements, but you can think it as 32 elements. So that's bank 0, bank 1 until the bank 32. So in each bank, you put element in this way. So 32 bits, that's 4-byte number. So in that case, for the first line, you can put 32 words, which is 128 bytes. So why I said there are more than 16 threads in a warp is executing is since in the previous situation, each thread accessed data in the bank interleavely. So it is not accessed. So the next thread is not accessing the next element. There is the stride 1. So in that case, if we have, so I think here, so in this case, thread 0 to thread 15 already access all one line number in the bank. So in that case, this one, the thread 16 will access the value 32, which is already in the second line. So there is the bank conflict. So when you access the value 0 and the value 32, I think I'll show this one much clearly here. The thread 0 and the thread 16, because the value 0 is here, and the value 32 is here. So the conflict happens when two threads access the same bank at the same time. So in this code, so what did we do here? Is we first load the left data, and then we load the right data. We do the operation like add, then we write back to the left side. So so all the threads perform the same load operation at the same time. All the thread loads the value on their left side. So there is the conflict. Do I make sense? If there's no question, I will go on to see. Yeah, so here before we can recall the shared memory bank conflict as you have learned from the last lecture. So if all the thread accessed here, if if each thread accesses a separate bank, there's no conflict. The third one is also no conflict, even it accesses the random number random number banks. But in the middle case, that's the thread 0 and thread 16 access the same banks. So the bank can only serve one request at one shared memory latency cycle. So if there's are two, so those two requests will be served sequentially. So how do we avoid these bank conflicts? So we can do this sequential addressing. So I can show here. So from what we have discovered, so the conflicts happen when threads, here, the conflicts happens the conflicts happens when the threads in a warp need to access more than one line of the address range. In that case, the thread 16 access the second line. So to avoid this bank conflict, the data accessed by a warp has to be the size of the bank. So there will be 32 words. So instead of doing the interleaved addressing, we make each thread access the next elements. So we can shrink the memory address to 32 words. So instead of accessing the thread 0 still access the value 0, and the thread 1, instead of accessing the interleaved, that is the value 2, we access the values 1, so next to the 0. So this is are the same. Here each thread will keep accessing the next location until we finish the first line. Yeah, this is the on the left side. Here is this one. So the left side the number is all this one from here. So we put all the left side number in one line, so that can be accessed without bank conflicts. Then we put the second left number in the next line in the bank. We put the left side in the first line of the bank and the right side number at the second line of the bank. So in this case, there won't be bank conflicts. Mm. So the stride, so we need to find the what's the stride. The stride is the distance between the first element in the left side to the first element in the right side. It's clear that that will be the size of the that will be the size of the bank that will be in is the 32 words. Here is a toy example, so you can see, you can think the bank in this case is only 8 words. 8 words. The size is 8. There are 8 banks. Yeah, it's clear to see here. So in real GPU, in if the compute compatibility is larger than 2.0, so the bank's number is 32, which means one line has 32 words. So um, uh, so this snippet of code just showing what we described how we do the sequential addressing. The S here is the stride. The stride used to be, as I said, is the if the data size is two times block dim, so the first iteration, the stride is half of the data size. Then at iteration, the stride will be divided by 2 as here. So the first is in the first iteration, the stride is 8, then become 4, become 2, then become 1. So here the thread, when the thread is 8, all the 8 threads will do the work. But when the stride become 4, only the 4 thread will do the job. That's why there is the TID less than the stride. Oh, there's one more thing I forgot to mention. Is this synchron? Is the sync thread here? Is why do we need this? Why do we need this sync threads? It's because first we do the thread sync across all the threads in a block. At the beginning of the for loop, when we first into the for loop, we do the synchronization. This synchronization has to be done because this shared memory copy. So we copy the data from global memory to shared memory. So each thread do their own copy. We have to make sure all the shared data is loaded to is loaded to the shared memory before we can continue work on this data. Or if you don't do that, some thread may already finish the loading the shared loading the copy the data to the shared memory. The other threads may still have random data or garbage data in the shared memory. So we have to synchronize that, make sure all the threads in a block finish the copy. but we still have to do another level of synchronization after we finish each level of the computation. I see this. So here we have to finish the first level, compare all the threads have to finish all their work. Then we synchronize all the threads, wait until they finished all their comparison. Then we can do the next level. That's why there's the synchronization at each for loop iteration. Here, so what I, yeah, that's the synchronization. Here is the same thing. So as I said before, there are idle threads. So half of the threads are idle on the first loop iteration. Yeah, that's what I said. But we can do something to make them do more work. Here is how we do. So the first snippet is how we do at the beginning. We have each thread bring their corresponding data from global memory to shared memory. But we want each thread to do more work than just bring the data. In this snippet of code, it brings the data from two locations and add them together. Those instructions are performed outside the for loop, which means each thread has to do these operations. That is where I said for. So here I think I have. This is the code. I just captured the content of the previous slides is what I said. How we, in this case, is that for each thread in the block, bring the data in two locations in consecutive blocks. You can see the start here actually is the first part of this one. So in this case, it's find the data in location I, also in the location I plus block dim dot block dim. It's already have the t here. Why this is make it more efficient is we move the first addition or the first level of operation outside the for loop. So that means So I will rephrase that. So we perform one addition outside the for loop. So we packing a little bit more computation to all the threads instead of that my loop start from just stride 1. We can start our for loop from stride 2. There's one more technique we can do to make this code become more efficient, is unrolling the last warp. So we don't need to do the synchronization once the active threads decreases under 32, because in a warp it guarantees that all the threads are executing at the same time. So that's here that is simply synchronized within a warp. So that means when we don't need sync threads, and we don't need to compare the thread ID. So let's see how it unrolls the last 6 iteration. So you write a separate device kernel. This is a device kernel. It's warp reduce, which is called from the global kernel. Here we call this device kernel. So in this device kernel, we still doing the same thing as we do in the for loop. We just do it one by one. The stride from 32 and decreases until 1. One more thing you need to be careful is the volatile keyword. You have to use this before the S data, which means the shared data. This volatile telling the compiler do not authorize the S data to regist file because it resides in the shared memory. So we operate all this thing in shared memory. So this is the final whole code. There are maybe one or more addition to do more to optimize the algorithm. You can take a look at it. It's we already cover all the steps. So we covered what is the parallel reduction. Actually, the goal is to summarize into one element from a given series of data. And you can perform different operations across this data. This is a bonus slide from Julian. It is discussing the efficiency of the reduction on CPU. We will skip it for now. Now let's move on to the second algorithm, second application, prefix sum. It's very similar to reduction. You are given a list of number, but instead of outputting one element summarizing this list, it output another list. You can see for example, you are given this list, then to generate the first number, you add all the numbers prefix this number. So 3 is still 3, And for the second number, it's 3 plus 1. For the third number, it's the 4 plus 7. It's 11. So you get how it works. It's very simple. So the naive parallel program can be written as this. So as I said, the first element already equal to the output, and then it calculate the second and third element by adding all the prefix number. Assigned each thread to do this calculation, so we can have all the numbers calculated together. But this is not efficient algorithm because do do many more unnecessary operations. We do more additions. So we can see here. This is a slightly better version compared with the naive version. This is similar to the reduction. We operate 2 by 2. So I think here is, I will show it here. So there are 8 elements. For the first step, we have to do, we have just add those two together. No, it's not that case. It's add this two together, this two together, this two. So add the next one. So there are 7 operations. So in the second iteration, it's doing the same thing. So you add this one with this. You add this one with this one, and this one with this one. So the steps between the two elements is 2. So before it is 1. Here is 0. Here's 1. And the next step is this one and this one. So the step is, or you can think that is 1, 2, 3, 4, 4. I think I can call this the first iteration is 1, the second iteration the stride is 2, the third iteration the stride is 4. So here is add the pairs of elements, stride elements apart. So that's 1 apart, 2 apart, 4 apart. But we're still doing lots of operations. I think that's from the operations we do. This is 7, this is 6, this is n divided by 2 at the last iteration. So we can see another even better one algorithm called I don't know how to pronounce it. This Bell Loach. This one is even better, but we have to do more steps. So on the left is you climb the tree. You can think it's like a tree, and then you go down the tree. So let's see how it works. This one is the left side, climb the tree. Is very similar to the reduction. You only add the element next to it. So and keep the so here is still 0, but there's 0, 0, 1, 2, 2, 3, 4, 4, 5, 6, 6, 7, and then you add the same thing until you find here you add the previous 4 elements. Here you have the second 4 elements, then you got the last element, which is the prefix of the previous eight elements. Once you have this element, this is ready, but you can see that all the previous elements still don't have the prefix number ready. You have to do more thing. First, you initialize this element to be 0, and swaps this element with you swap this element with the that is I think the stride is 4 because it's divided by 2. You swipe the number 4 apart, or you can say assign 0 to here and put this x 0, 0, 1, 2, 3 to here. That is one level. So once you finish that, you do another, the second level, the stride become 2. You still swipe this element to here, and here you have the 0, 1, 2, 3, and you I think is you swipe and add the, so you put 0 to here, like you swipe the 0 and this element, then you add this element and 0 and put it here. Here is the same thing. You put 0 here and the addition is here. So the addition for those two is from 0 to 5. The last level, the stripe become 1. You do the same thing. So for this, take this for example. You swipe this to put it here and add those two addition. You do the addition of these 2 elements and put it here. It's not very difficult. It's easy to understand, but it takes a while to implement this algorithm. Here give a list of applications which use the prefix sum internally. It's very popular. I can give a very simple example. It's like the running balance of your bank account. You have some deposit withdrawal. So this number will be a list, but you want to see the current balance in a long run. That in order to get those numbers, you need this prefix sum algorithm. It's very commonly used. So the third application is histogram. Histogram basically here is a graphical representation of the distribution of numerical data. Think you are given a list of number. You bucket this number into specific position. Here is an example. You have a list of data array called the measurements array. So the compute bin is a function you can see, you can think of. You give an element, you give one element in this measurement array, and it give you the number of bin. Then you increment the results in that bin by one. So yeah, it's easy to see how it is implemented. The D in is the measurement we have. So we use the module the number of the element module the number of bin. It will give which module this element belong to. Then we increment the increments the number in that of that bin. So, but there is one problem. What if, for example, if one bin current value is 0, you have thread 0 and thread 1 both handle a number, and the result of that number points to the bin or the bucket 0. So both thread 0 and thread 1 would like to increment 0 to become 1. So what would be the final result? It's hard to say. It can be 0, can be 1, can be 2. That's in this figure show what is called the risk condition. How do we, I think, yeah, how do we avoid this mechanism? So what's the mechanism to avoid this risk condition? Is using the atomic add. I think we discussed from the last lecture. The atomic operation will lock down, will lock each steps. So each thread will read the value, increment, updated, and write back to the value. Those 3 steps will be executed as atomic, so that will be executed as a 1 unit. No one can disturb these 3 steps. That will be executed, that will be finished at once. Here is we add the atomic add operation over this increment instruction or increment code. It's, as I think Trinanian said, the shared memory supports the atomic operation. So each thread, once each thread is going to see, increment this value, but the atomic add ensure that this value will be added one by one. This showing that if the if you have a big histogram data set, it it can be it can be split into small group of number and do the local histogram and do the reduction. That's as we discussed in the reduction algorithm. Mm. Here the question is, do we need the atomics to manage the access when we try to reduct the element when we try to redact the partial results for each bin, like we for this blue bin, we try to redact the number and into one number. So the answer is yes, we still need to have the atomic operation. Mm. Mm. This is so just a few things about the histogram using atomic operations. Uh, for for yeah, this is still for the histogram also, for the local histogram, and do the reduce, put the result into the global memory. Mm. The last application is convolution. It's a very popular uh, array operation that is used in various forms in signal processing, digital recording, and lots of. I think it's very popular in the deep neural network. I guess most of you have heard about that. Um, uh, it's the concept of it is not very hard. Uh, so the convolution is used performed as a filter that transforms signal or pixels into more desirable value. So I would interpret it as the convolution is performed to see the effect of a transformation over a series of data. We will see that later. This showing that using the 2D convolution in the image processing, we can detect the boundary of the image. It's detected the piece the number of pixels. I think in the image processing lecture, you will discuss more about this. What does the convolution perform? It does the weighted sum or dot product of the neighboring elements. It's better to see this example. This is a 1D convolution example. So this M array is, I think I'm running out of battery. This M array is a mask or a filter. So each thread have this array. So the N is the input data we have. In order to generate the output number in the corresponding position, we basically do the dot product of those two array. So 1 multiplied by 3, we get 3. Then 2 multiplied by 4, we get 8. These are the intermediate product product of those elements. Then we do the sum. Then we put the result into the output array. This is similar. Then after we finish the position 2, we move on to the position 3. We will move this mask one element to the right. I think we'll see. This is the casual. This is the FIR algorithm in mathematical formula. I think X is the input signal, Y is how we get the position, the Y, the output at position N. So the BI is the value of the filter array. N is the size of the filter. The FIR filter is very similar to the convolution, or it's another way of the core idea is doing the convolution. It's a very popular signal processing algorithm. So when we calculate the output, for example, for the position 1, so there's no element we can multiply with 3, so we need to pad this element with 0. So it's called a ghost element or 0 padding. So in that case, we can just multiply 0 by 3, 1 by 4, and do the summation. The 2D convolution is the same concept. So instead of 1D array, the mask or the filter become a 2D array. Then we do the dot product of those two matrix and generate one element, generates output of one position. Then we shift the element, we shift the mask over the matrix and calculate again. So the same thing if we try to calculate this position 1, 1, we need the 0 padding to be able to multiply with the mask. So if we try to calculate position 1, 0, we need more 0 padding over here. So here it's about how we put our data into the different blocks, and when they are in different blocks, how we access the neighboring elements. I will leave this to the lab section because in tomorrow's lab you will work on an application. I think it is very similar to what's described in this picture. So once you look at the lab and have some thoughts, I will keep talking about how we deal with this case, how we find the correct neighboring elements. Yeah. So that's all for today's lecture. Thank you. Does anyone have question?